Good morning and welcome. So today we're going to go over section 4.1, which is going to have us finding critical points and other things regarding a graph and trying to evaluate and maximize or minimize a function. We're going to start out this way though. We're going to start out with this little piece of paper, and I've got several copies of this. So we've got a grid of 14 squares this way and 18 squares this way, and my goal is to cut out some corners and fold this up into a box. So for instance, like if I cut out just two corners here, or a 2x2 corner here and here, I can fold this up into a box. My goal though is to try and find the maximum volume that I can contain in this box. So how could I do that? Well, we're going to use calculus to try and help ourselves out here a little bit. So if I fold this up into a box, then it's going to be an open-lidded box, and we can calculate the volume of this box. So let's work on calculating the volume of that box, depending on how many squares I cut out. So let's see. Let's control or calculate the volume, V of x. Well, let's see. I'm going to be cutting out a certain number of squares, so I'll call that x. So that's going to be the number of squares I cut out. And then in the one direction I have 14 squares, and I'm cutting them out here and here. So I'm going to subtract 2x. And from the other direction I'm subtracting 18 minus 2x. So that's a formula that tells me the volume of my box. Now one of the things that we want to pay attention to when we're creating this box and looking at the possible values of x is the domain. So as far as the domain is concerned, I mean, this is a polynomial. You could argue that the domain is everything, but in practical purposes, for us, the domain is going to start at 0. We don't have a box if we don't cut anything out. So technically there'd be a parenthesis here. I'm going to put a square bracket just for my other purposes. The most I could cut out, if I cut out 7 squares, then I'm going to cut all the way to the middle, so that's kind of like the most that I can cut out. So there's the best I can do. Now as far as working with this a little bit and trying to figure out, well, what's the maximum volume I can cut out, that's a good question. You can see that you get a couple different shapes. Mind folding that one up a little bit for me? Thank you. And the question is, what's the volume? So let's graph it. Let's put this in on Desmos and graph it. So I'll call it V of x equals x times 14 minus x, or 14 minus 2x times 18 minus 2x again. This is going to be some polynomial graph. I really only care to see it between 0 and 7. You can see that this polynomial actually touches here, touches the x-axis at those 2 points. So somewhere in here is the maximum value for this function. Now when you're maximizing functions, you're going to always have to check these endpoints and any critical points, any points in between. So somewhere between, say, I don't know, it looks like 2 and 3, this function should have a maximum. That is, you're going to get the maximum volume out of this. And that's good because, I mean, there's a lot of ways you can cut into this, but only one of them is going to give you a maximum. So let's understand a few things about this problem, and then we'll investigate it later. One of the things we need to understand is something called critical points. So let's look at critical points for just a minute here. So on the right-hand side of this, I've got this little graph with points at A, B, C, D, E, etc. And critical points for us, there's going to be some interesting things happening at critical points. All of these points here, B, C, D, and E, are critical points. One of two things is happening at those critical points. Either you're going to have a zero tangent line, or what about this part, this point right here? I mean, we got a nice zero tangent line here, here, and here. But why do you think this would be a critical point? What could I say about the derivative here? Doesn't exist. Good. That's that corner point that I talked about last week. That is, you're going to fail to have a derivative if the function's not continuous, or if it has a corner point or a vertical tangent. In this case, we've got a corner point. So let me give you a little bit of a definition. A critical point or a critical number is a place in the domain where the function either has a zero derivative or the derivative does not exist. So those are the points in which interesting things happen in a function, and that's where we're going to want to look when we're trying to find interesting behaviors of a function. So a critical point is a value C where f prime of C equals 0 or f prime of C does not exist. One of those two. So we'll start out today looking for critical points, and then we're going to move on a little bit to try and find the maximum or minimum of a function. And those maximum or minimums are going to occur at one of two places, either at the endpoints of your domain or at a critical point. That's the only place you're going to get those minimums or maximums. All right, so let's take a look at some of the problems to start with here. So this is for your handout from the other day. I hope you still have your section 4.1 handout. So we're looking for the critical points of this function in this interval, negative 3 pi over 2 to 3 pi over 2 for cosine of x. So, okay, let's work on that. So that'll be example A here. So we've got f of x equals cosine of x, and that's going to be between negative 3 pi over 2 and 3 pi over 2. Well, the first thing to do is to find where the derivative is actually equal to 0. What's the derivative of our cosine function? Negative sine. Good. So f prime of x equals negative sine of x. And I want to know, where is the sine function equal to 0? Well, that's going back to trigonometry, isn't it? So, wow, that's not fair. Let's see if we can't figure out where the sine of x is equal to 0. Actually, we got minus sine of x, but does the minus really matter in this equation? If I divide out by negative 1, I end up with sine of x equals 0. Sine was which coordinate of your points on the unit circle? It was the y coordinate. So I want to know where the y coordinate is 0. And that's going to happen at one of two places. So it's going to happen either here or here. What are those angles in terms of radians? 0 and pi. And then, well, 2 pi is actually beyond that. And let's see, minus pi would also be in this as well. So those look like the 3 points that would actually satisfy this. We can kind of double check ourselves with Desmos. Do it this way. So take a look at the graph of y equals sine of x. And I'm going to have to change the scale a little bit here. Let's put in some labels of, let's see, how about pi over 2? There we go. I want to know where that's equal to 0. And we've got 1, 2, 3 points in the range of negative 3 pi over 2 to 3 pi over 2. So nice. Those are our critical points. So our critical points negative pi, 0, and pi. Nice. Let's work with the next one. And the next one is going to show you a little bit of a trick in terms of factoring and working with your derivatives. So for the next one, let's see, let me get back over to here. We want to find the critical numbers of this function right here. So it says, all right, let's find critical numbers of x to the 8th times x minus 2 to the 7th power. Okay, we'll work on that. So example B, f of x is x to the 8th minus x minus 2 to the 7th. What rule am I going to have to use to differentiate this? Product rule. Good. So you've got, this is kind of like your f, and that's your g. We need f prime g plus g prime f. So let's work on that. F prime of x. F prime of x is going to be 8x to the 7th times x minus 2 to the 7th plus, how about g prime? What's g prime going to look like? Good. What's the derivative of the inside? 1. You do have to use a chain rule here, but in using the chain rule, you get the derivative of the inside as 1. So if you happen to forget, it wouldn't have mattered in this case, but do kind of keep in mind you still are using the chain rule. Times our x to the 8th power. Now, polynomials are going to be differentiable everywhere, continuous everywhere. We're not going to have a place where the derivative is not 0. So I am going to have to find where the derivative equals 0. And that's a little bit of a chore until you get this thing factored. So there's a nice little trick in terms of factoring this. Can anyone suggest something before I give it away?
X minus 2.
Say again?
X minus 2.
What about the x minus 2?
Factor it out.
All right, is there anything else I can factor out? Yeah, I've got x to the 7th, which I can factor out. How many x minus 2's can I factor out? 6. Now, if I factor out 7 of these, that's going to leave behind an 8. And I'm taking out 6 of these, so that'll leave behind an x minus 2. And then, how about here? What's left behind after I factor out the GCF from there? 7x. So that's looking a little bit better. X to the 7th times x minus 2. How much of this stuff do you want to do in your head all at once? If you distribute the 8, you get 8x minus 16 plus 7x. 8x and 7x is going to give you 15x. Nice. So now you've got it completely factored. It's a little bit easier to see where this is actually equal to 0. Let's take a look at where it's actually equal to 0. Right here, that's pretty easy, right? That equals 0 and x equals 0. Where else? At 2. Great. And then this one, well, maybe you have to set it equal to 0 and solve, but you're going to get x equals 16 over 15. Now, annoyingly, just kind of giving you a heads up, when you put your answers into WebAssign, a lot of times they'll do this stuff, and that is they'll ask you to put them in order. I don't know why they can't just check. All right, there's only 6 possible orders you could list it in. It wouldn't take but a nanosecond to check that. In any case, those are your critical points. Are you okay with our little factoring trick there? That's something that I would suggest that you know. So, thumbs up on that one? All right, good deal. Let's keep moving. Let's move on to example C here. The graph of a function that is continuous on 1 to 5 has the given properties: an absolute maximum at 2, absolute minimum at 5. 4 is a critical number, but there is no local maximum nor local minimum there. So that's kind of interesting here. We've got a critical number, but it's not a local max or local min. And if you look at 4 in either graph, maybe you kind of see why. So what you've got there is something called an inflection point. The graph kind of changes. It's still a decreasing function, but it's changed its shape a little bit. It went from concave up to concave down. It has a zero derivative here for just an instant. That's okay. So that's what makes it a critical point, but it's neither a maximum nor a minimum. Now both of these graphs have a maximum at 2. So maximum at 2, all right, that works. Absolute minimum at 5, all right, so absolute minimum at 5, that works. Actually, it works for one of our graphs. Absolute minimum at 5. Absolute minimum means the minimum for the entire function. So one of these graphs doesn't actually satisfy the fact that it has an absolute minimum at 5. Which one has an absolute minimum at 5? So the lowest that the function get is when x equals 5. Yeah, the left one. Because over here, the absolute minimum is at x equal 1. So that one's not, that one doesn't have the absolute minimum at 5 as it's supposed to. So there's your absolute minimum. So both of them have the absolute maximum that they're supposed to, just this one doesn't have the absolute minimum that it's supposed to. Let's move on down to example D. Try and introduce and really drum home a little bit this idea of absolute maximum and absolute minimum. So it says sketch the graph. Use your sketch to find the absolute and local maximum and minimum values of f. Note the right hand side as an endpoint that's got a hollow dot here. So nice little hollow dot. What does that mean in terms of the graph? What's that hollow dot mean?
It can't be pi over 6.
That means there's a hole there. It's not defined there. So that the graph just doesn't exist at this point. It stops before we get there. So it says this up to, but not including pi over 2. So we do have a local minimum or an absolute minimum. So the absolute minimum of this graph, absolute min, is 0 at x equals 0. And as far as the absolute maximum, this graph doesn't have an absolute maximum because it never quite gets to 1. It gets close to 1, but that point of x equal 1 is actually not on this graph. So undefined, does not exist. Ethan?
When you say it doesn't reach 1, do you mean on the x or the y?
On the y-axis. Yeah, so it doesn't quite reach 1. Because you never get to pi over 2, which is where you have to get to in order to get that value. Yes?
When you say absolute, do you mean like, does it have to be a whole number, or could it be like?
It could be an irrational number, it could be a fraction, it could be a decimal, whatever you want. When I say absolute max and absolute min, sometimes I use the word global max, and global min. You'll hear me use that occasionally. That's probably because that's the way I learned it. It means throughout the entire function in its domain, what's the biggest that it gets, what's the smallest that it gets. So I'll use those interchangeably. I'll try and stick to absolute max and absolute min because that's what this book uses. But if I lapse, then just understand that I really mean the same thing as absolute max and absolute min. Now that's in contrast to, say, a local min or a local max. Let's look back at this function here. And I have to scale out my graph a little bit. There you go. This is a local max, and this is a local min. Now, why are there local mins and local maxes? Well, the function actually does get bigger than this. It's just that nearby, this is the biggest thing going. So the function doesn't get any bigger than this for nearby points. Same thing over here. It doesn't get any smaller than this for nearby points. Does it get bigger than this overall? Yeah, absolutely. You can keep on going as high as you want, or you can keep on going as low as you want. That's why these are local maxes and local mins, respectively. So those are a little bit different than your global max. So your
Parameter for the nearby points, like is it like an interval away or?
Yeah, just some positive interval, some positive neighborhood is one of the fancier terms that they use for this. But it's just some area around this where it's the biggest thing going. So any positive radius you want to give it, is, as long as it's the biggest thing in that positive radius, it's a local maximum.
So the local maximum is whatever like the graph is cut out to be?
It's whatever it peaks at here or down here. Those are your local mins and or local max and local mins.
Oh, okay, so like the 7 pi over 2, we wouldn't consider a maximum because we don't have a peak?
Pi over 2 is not a maximum because it's actually not
Oh, I'm
part of the
talking about
graph.
on the other graph.
Oh,
So like 7 pi over 2, it just kept going up, so we don't have a peak there, right?
yeah, it just keeps on going up and up and up and up. It doesn't stop. So there's no,
Way to calculate.
yeah, there's no actual maximum of this graph because it goes on and on forever. So its maximum would be infinity. James?
Is it undefined or would it be infinity?
I guess I would kind of regard it as infinity.
Okay.
I'm not sure that that's something that WebAssign is going to ask you, what's the global max, and expect infinity. I don't think they would.
So
No.
think globally, not globally.
Yeah, exactly. All right, let's keep going. Flip side here. There's a little factoring trick that you're going to pick up as we do example E. So try and figure out that. Let's roll with this one. So example E. I'm going to replace the t with an x. So I'm going to call that h of x equals x to the 3/4 minus 2x to the 1/4. And this looks pretty fine. You know, it looks okay. No big deal. Let's take a look at the domain. You can see the domain from the graph here, right? Does the domain include 0, 0? What do you think? Yeah. So our domain would be from 0 to, well, infinity. This graph is defined for a long, long time.
But there's a hollow, is that a hollow dot at 4, or is it just a grayed out dot?
No, it's just grayed out dot because that's where it's crossing the x-axis.
Okay.
Because we keep on going there, I think. So let's find our critical points. Now our critical points have to be points that are in the domain. It doesn't do us any good to look for critical points when the function is not defined. So h prime of x, 3/4 x to the negative 1/4 minus 2/4 x to the negative 3/4. And this is a little bit messy, won't lie. Let's see what we can do in terms of cleaning this up a little bit. It is going to require a bit of work. I'm going to start by putting these terms in the denominator. 3/4 x to the 1/4 minus, I'm not sure if I want to put this in lowest terms or not because right now we've got common denominators. I'm going to hold off for just a minute. 4x to the 3/4. Now these fractional exponents are a little bit of a pain here. So let me see if we can't get rid of them, at least from the denominator. So I've got x to the 3/4 here and x to the 1/4 here. If I multiply by something so that I can get rid of this exponent, I'd have to add something to it. What would I add to 3/4 to get up to, say, 1?
3/4.
Yeah, 3/4. So let's do this. I'm going to multiply by x to the 3/4 over x to the 3/4. I'm going to do the same thing over here. 2 over 4x to the 3/4. This time I'm going to multiply by x to the 1/4. And let's see what that gives me. That's going to give me 3x to the 3/4. I'll have a 4x in the denominator here, and I'll have a 4x in the denominator here, minus 2x to the 1/4 here. Okay, so I've cleaned this up a little bit. I want to know two things. I want to know where the derivative is equal to 0 or is undefined. So let me see if there's anything more I can do here. In terms of cleaning this up a little bit more, I can. Let's look in the numerator. Is there a common factor in the numerator?
1/4.
X to the 1/4. That's going to leave behind 3x to the 1/2 minus 2 over 4x. That's our derivative. So the question is, where is h prime of x equal to 0 or undefined?
Undefined is there.
Yeah.
X equals 0.
So it's undefined where the denominator is 0, and it's equal 0 where the numerator is 0. All right, so we're going to take x equals 0 out of this because we've already got x equals 0 as part of our answer from the bottom, or from this part. But what we have to do is figure out, well, where's the numerator equal 0? So basically, where is the numerator equal to 0? Okay, let's work on that part. So I want to know where 3x to the 1/2 minus 2 equals 0. So that's where our numerator equals 0. So that's going to be 3x to the 1/2 equals 2, or x to the 1/2 equals 2/3. How are you going to solve this?
Square root.
Well, this is a square root already. X to the 1/2 is a square root. Square both sides. Good. So if you square both sides, I get x equals 2 squared over 3 squared, or better yet, 4/9. Does anyone know the decimal for 4/9? Don't look it up. I'm just asking. I'm just curious. So it's 0.444444. It's kind of cool when you're dividing by 9, or take 1 and divide by 81. You get a cool decimal expansion there. Let's look at the graph of this and see if it makes sense. And let's see, my aunt's signed in. Yes. So I should be able to pull up 4.1. So yeah, here we go. So the nice thing about Desmos is it can find points for you like your x-intercepts, etc. But it also finds these minimum points. Now, unless you're really adept with your decimals, you might not look at that and go, oh yeah, that's 4/9. But take a look at the decimal that we get when we click on that. It is the decimal for 4/9. So nice. What about 0? Is 0 a critical point? Yeah, 0 is a critical point because you've got an undefined tangent there. Why do you think the graph has, or excuse me, the derivative doesn't exist at x equals 0? What do you think is going on in words?
Vertical tangent.
Yeah, you got a vertical tangent. That's perfect. That's exactly what's going on here. You got a vertical tangent. So our critical values are 0 and x equal 4/9. Well done. Well done. So our critical values . 0 and 4/9. Nice. Okay, let's continue to work with some more and more messier ones. For instance, f of x is 16 cosine of x plus 8 sine squared of theta. This is going to give us a chance to practice with our chain rule here. And hopefully you'll recall really what this means. It's 16 cosine of theta plus 8 times sine of theta squared. So it's kind of some funny notation that we allow ourselves in mathematics, is to put that square there to really mean this squared. This is what you should be looking at and thinking about when you differentiate here. So example F. We've got f of theta equals 16 cosine of theta plus 8 times, I'm just going to write it as sine of theta squared. Take your best shot. Do the derivative. See what you can come up with. So if you're watching this later, you can pause the video. I'm going to change my screen on Desmos. There. Oops, turn it. There. Derivative of cosine. What's the derivative of cosine? Negative sine. Thank you. All right. Negative 16 sine of theta plus 2 times 8 is going to give me 16 again. Sine of theta, this time to the first power. Is that it? Times derivative of the inside. You got to use the chain rule, derivative of the outside, gives me the 2 times that to the first power times derivative of the inside, which is going to be cosine of theta. Okay, great. I still want to know where that's equal to 0. It's going to be defined everywhere. We're not going to have any problems with the domain. We just want to know, well, where is it actually equal to 0? So how would you solve this? What would you do if you were stuck solving this thing? What could you do?
Factor out 16 sine.
Yeah, factor out the GCF, right? So I'll factor out a 16 and a sine. So that's going to leave behind, let's see, 16 sine of theta. It's going to leave behind negative 1 plus cosine of theta equals 0. And probably one of the most powerful ideas that you have in your mathematical toolbox is when you multiply two things together and get 0, one of them has to be 0. That doesn't work with any other number. So either 16 sine of theta equals 0, or negative 1 plus cosine of theta equals 0. Sine of theta equals 0, we've already looked at that today. That's going to happen at these kinds of points. So 0, pi, 2 pi, 3 pi, basically at n pi. So theta equals multiples of pi. And over here, Well, I move that 1 to the other side, I get cosine of theta equals 1. Where's the cosine of theta equal to 1? Cosine was what coordinate? Cosine is your x coordinate on the unit circle, and your x coordinate on the unit circle is going to be 1 right over here. 1 and 0. Yeah. At 0, and at 2 pi, and at 4 pi, and at negative 2 pi, and at negative 4 pi. Basically, multiples of pi. 2n, or multiples of 2 pi, I should say. So, now, this set contains this set. So it's just enough to say that, yeah, at multiples of pi, you're going to get critical points. What should I see when I look at the graph at those multiples of pi? What do you think?
We should cross the x-axis.
Maximums and minimums?
Yeah, maximums and minimums, right? So, and if you look here at multiples of 2 pi, the graph gets really flat because you really have a couple things going on there. But even at multiples of pi, you know, your odd multiples of pi, you're still getting your minimums. Over here at 2 pi, you get your maximums, etc. So, yeah, it all lines up and makes sense. Nice, nice. Let's expand on this a little bit more. We're going to start trying to find the minimum and maximum of a function on a closed interval. So that would be problems like number G here. It says find the absolute maximum and absolute minimum values of a function on a given interval. So this is a little bit different. It's saying, okay, you've got this fixed range of numbers. I don't care about the function elsewhere. I just care about the function on this interval. So like our beginning example that we started out this section with, when we're looking at that polynomial that told us the maximum value or the volume of our box, we don't care about the function beyond 0 to 7 because we can't really make a box if we don't cut out something, and the most we can cut out is 7. So really these should be parentheses, but I just use brackets because here, when you're evaluating these things, there's 2 sets of points you have to look at. And let me be very clear about this. I test you on this. In order to try and find the maximum, global max, or the absolute max and absolute min, you're going to have to look at the endpoints and any critical points and evaluate the function at both sets. So let's do example G and see how that works. So example G. F of x is 6x to the 4th minus 8x cubed minus 24x squared plus 1 on the interval negative 2 to 3. So the first thing we're going to do is find our derivative. That's going to be pretty easy because it's a polynomial. Polynomials are just so wonderful to work with. They really are. We do a lot of work with them because of this. So the derivative here, I don't think I'll bother asking you for it. I think you can calculate it pretty easy. 24x cubed minus 24x squared minus 48x. That's our derivative. If I want to know where that's equal to 0, then I could factor out a 24x. And that's going to leave behind x squared minus x minus 2. And that factors a little bit further. X minus 2 times x plus 1. So where's this thing actually equal to 0? What's the solution to this? Nice. So there's where it's actually equal to 0. Now to find the maximums and minimums, you have to look at 2 sets of points. You have to look at the endpoints here and you have to look at the function there. We don't need to look at the graph at all. All we need to look at, the function, is at these points. So let's make ourselves a little table here. And I'll put them in order for myself. Let's see. I want to go from -2 to -1 to 0 to 2 to 3. Now you may get the idea that, oh, I'll just put in all the integers. I don't want to see that. What I want to see is you evaluating exactly and only the points that we need to, which would be these particular values. So let's take a look when we do that. Now, in case you haven't played with it before, you can do that in Desmos. So what I did is I defined this graph, or this function, like this. Then I can make myself a little table. I can plug in -2, -1, 0, 2, and 3. So nice. Let's fill in our little table here. We get 65, -9, 1, -63, and 55. So the functions changes certainly pretty wildly between 2 and 3, right? You go from -63 to positive 55 in quite a short breath. So let's actually graph this now and see if that makes sense compared to everything else. So let's get rid of this. Make that a 1. There you go. There's your graph. Looks okay. You can see that the overall maximum is right here, and the overall minimum is right here. So you've got an absolute max and an absolute min. Absolute max is at -2, so the max is 65, and the min is -63. Nice. But please check both sets of points, because you never know where you're going to find your max or your min. Could be at the end points, could be someplace in the interior. You just don't know. Okay.
And for us, we would just use the table function on our TI.
Yeah, you can use the table function on the TI graphing calculator to do exactly what I just did there. Absolutely. Yep. Oh, yes, go ahead.
Last question, for the max and mins, you don't want like the exact point, like -2, 65, you just want.
Yeah, so, I'll try and be careful to ask for what I want. A lot of times it's just the max or the min, so I'd want the y coordinate. Sometimes I'll say, well, where does it have its maximum, or where does it have its minimum? And in that case, I'm looking for the x coordinate. So, nice distinction there for me. Thank you, Christian. Yeah, sometimes I want one versus the other. Yes?
So if you set the intervals with parentheses instead of brackets, so the points weren't included, should they even bother testing those points?
If your interval actually has parentheses, then no, then you wouldn't be testing those endpoints. So for our first example, going back here, this really should have parentheses. You don't really have to test the endpoints because of the parentheses, because they're not really part of the domain of this function. So you wouldn't be testing them there. So you'd only test the critical point. When you multiply this out, yeah, the critical point doesn't turn out to be something you can solve very easily for. So we'll look at that maybe with Newton's method when we get to that. Almost done here. More tricks in terms of factorization and stuff. Let's take a look at example. We're running out of time here, at least the time that I want to spend. Let's work on example I next. So example I. Again, I'm going to change it to f of x equals x times the square root of 4 minus x squared on the interval -1 to 2. Now we're going to rewrite this as 4 minus x squared to the 1/2. This is a nice problem just to differentiate and clean up. What are some of the rules you're going to have to use in finding the derivative here?
Chain and product.
Chain rule and product rule. All right, so the first thing you do is the product rule. And even though that's just a little x, that's your g, or that's your f, that's your g. Let me take a moment and write, what g prime is going to look like. G prime of x, well, you got to differentiate the outside times the derivative of the inside. So the derivative of the outside is going to be 1/2 times 4 minus x squared to the negative 1/2. That's the derivative of the outside. What's the derivative of the inside? Yeah, negative 2x. Thank you so much. And that 2 and this 2 can cancel each other out. That'll leave me with a minus x. And then this term has a negative exponent, so I'll take that into the denominator. I'll rewrite it as minus x over 4 minus x squared to the negative, or excuse me, actually it would be positive 1/2 now. Okay, let's put this together and see if we can't come up with a derivative. So the derivative of f is just going to be 1 times 4 minus x squared to the 1/2 plus x times this, which is our g prime, minus x over 4 minus x squared to the positive 1/2. So these two combine and I get 4 minus x squared to the 1/2 minus x squared over 4 minus x squared to the 1/2. And unfortunately, solving this as it is kind of a little bit of a pain. So I'm going to play the same trick that I played earlier. Well, actually a different trick, I guess. I need to get common denominators. What's a common denominator between these two? Yeah, basically this denominator here, right? Because this denominator is 1. So what I'll do is I'll multiply this by 4 minus x squared to the 1/2 over 4 minus x squared to the 1/2. What does that give me over here? So the denominator is just going to be my 4 minus x squared to the 1/2. How about the numerator?
It's just 4 minus x squared.
Yeah, it's 4 minus x squared to the first power, right? Because these have the same base. So you keep the base and then add the exponents. So that's going to be to the first power, which we don't need to write because it's just to the first power. So we'll get rid of that. Thank you, Christian, for these really awesome markers. Nice. So now we've got like terms. We can combine these and get 4 minus 2x squared over 4 minus x squared to the 1/2. Okay, so we need to find the critical points. The critical points are going to be where the denominator, where the derivative doesn't exist, or where the derivative is 0. So the derivative equals 0 where the numerator equals 0. And the derivative does not exist where the denominator equals 0. So those two sets of points Can you eyeball where the denominator equals 0? What value is going to make the denominator, what values is going to make the denominator 0? 2 and negative 2. Now negative 2 is outside of our area of interest, so we don't have to worry about that one. 2 is already an endpoint, so we got that one. So the last thing to do then is to figure out where the numerator equals 0. That's going to be 4 minus 2x squared equals 0. Personally, I find it easier to move the 2x squared to the other side as opposed to the 4 to the other side. What do you think I like about moving the 2x squared to the other side? It becomes positive. Divide both sides by 2. You get x squared equals 2. So x equals plus or minus the square root of 2. Don't forget both of them. Square root of 2 is about 0.414 or 1.414.
Which the negative falls outside of range, right?
Yeah, the negative one falls outside the range. So the negative is outside of negative 1 to 2. So we don't have to worry about that one. As far as testing points is concerned, all we have to worry about is the positive root and the endpoints. So we'll make ourselves a little t-table there. Tell you what, I'll do this one on the graphing calculator just for something a little different here for us. So let's clear out this stuff, clear up that. Make sure you put in your function. Don't put in the derivative. Square root of 4 minus x squared. Looking pretty good. You should have your table set up the way I do, set with independent set to ask, dependent set to auto. That way you can fill in the values of x that you want. We want values at negative 1, square root of 2, and 2. And let's see what happens. So let's go up here to table. I'm just going to delete all these things. Negative 1. And let's type in the square root of 2, square root of 2. Now this nice symbol is going to disappear. It'll give me a decimal value, but at least I'll get the correct decimal value over here. And finally, 2. So, bingo. So let's put a little chart there for ourselves. So we have negative 1, square root of 2, and 2. Values of... Does anyone recognize this decimal value? Yeah, root 3. Nice. Wow. Ooh, impressive. Well done. Now he has to find the absolute minimum and absolute maximum values. So absolute minimum, that's going to be negative square root of 3. And, oh, excuse me, that's absolute minimum here is going to be negative square root of 3. Absolute maximum is going to be at 2. Nice. Nice. Okay. How are we doing on that one? Doing pretty good? Keegan? Thank you. Alex, thank you. Yes?
So, since we have this bracketed, would we have to write an interval notation for the absolute min and max, or no?
No. No. Just, yeah. Just good enough. Just list the values there. Okay. Cool. Let's put this one in the books.